So, hello everyone. So today I would like to talk about 6-axis force torque sensor using laser processing. In recent years, tactile sensors have been studied and developed in various fields. For example, they are used for robot hand control and surface texture detection. In this situation, it is important to simultaneously measure shear force and torques as well as surface pressure. For these reasons, a number of MEMS multi-axial force sensors have been developed, focusing on multi-axis force detections. These sensors have the advantage of very small, high accurate, and sensitive. However, the fabrication process was complicated. On the other hand, physical sensors based on laser-induced graphene, which has simple fabrication process, have attracted attention in recent years. LIG is porous graphene obtained through direct CO2 laser irradiation to polyimide under atmospheric condition. In addition, the LIG changes its electrical resistance to strains. So LIG has been applied to various physical sensors such as pulse wave sensors and wind speed sensors because of its easily formed piezoresistive layer. Currently, many of these sensors use a simple planar structure and mainly for single-axis measurement. Therefore, LIG physical sensor could be further developed if multi-axis measurement using 3D structure become possible. So, in this study, we propose a 6-axis force torque sensor using a laser fabrication process and thermal deformation. The proposed force torque sensor consists of 4 pairs of standing LIG cantilevers covered in an elastic body. Our device has 2 advantages. The first is a simple fabrication process. The second is the ability to form the multiple 3D sensing elements directly on the substrate. The proposed sensing element is formed by using UV laser irradiation, CO2 laser irradiation, and thermal deformations. We use the PI film as a starting material for the sensing element. The UV laser was used to accurately process PI films into device shape with low thermal effect. The CO2 laser was used to directly form LIG strain gauges at the root of PI cantilever. Then, cantilever is heated at high temperature while in a standing position. Due to the thermoplasticity of the PI film, the cantilever maintains a standing position while even at room temperature. Next, I would like to explain the biaxial force detection using pair of standing LIG cantilevers. When normal force is applied, both cantilevers deform downward with elastic body deformations. The deformation of the cantilever causes both LIG to extend it. So both LIG show a positive resistance changes. On the other hand, when shear force is applied in the left direction, the right cantilever deforms downwards and left cantilever deforms upwards. Then the right LIG is extended and left LIG is compressed. So the right LIG shows a positive resistance change and the left LIG shows a negative resistance change. So therefore, biaxial force can detect using a pair of standing LIG cantilevers. Here we define the 8 cantilevers of the proposed force torque sensor as R1 to R8. For the shear force in the x-axis, R4 and R7 show positive resistance changes, and R3 and R8 show negative resistance changes. When a z-axis force is applied, all cantilevers show positive resistance changes. For the torques around the x-axis, R2 to R5 show positive resistance changes, and the rest cantilever show negative resistance changes. For the torque around the z-axis, all cantilevers show alternating positive and negative responses. Therefore, 4 pairs of cantilever can measure 6-axis force and torque from the response of the resistance change. Now, I would like to explain the design and fabrication of our proposed sensor. The sensing element is 30 mm square PI film with a thickness of 200 micrometer, and each cantilever has width and length of 3 mm. Also, the front surface of the sensing element is roughened to improve the adhesion to the elastic body, except for the energy strain gauges. Here we show the design of the fabricated sensor. The standing sensing element is located on an acrylic base, which is covered with the PDMS silicon. The dimensions are shown as such. Here we show the fabrication process. First, the flat sensing element is formed by two types of laser irradiation. Next, the sensing element is sandwiched between the pyramid-shaped aluminum housing and heated at 220 degrees Celsius for an hour. Then it was connected to the copper wire. Finally, the sensing element was covered with the PDMS by molding process. So now I'll show you the UV laser processing. First, the film surface was roughened by the cross laser irradiation at low power. Next, the high power UV laser was irradiated to cut out the cantilever shape. Finally, it was cut out a square shape. Then I will show you patterning the energy strain gauges by CO2 laser irradiation. The piezoelectric layer is formed in a few seconds. Here we show the housing used during thermal deformations. 4 pyramid-shaped protrusions are formed on the housing surface. Here we show the fabricated sensing element. The width of the UV laser cut line was 30 micrometer. Also, the energy strain gauges were formed correctly. And the standing angle of the old cantilever was 32 degrees. Here we show the fabricated sensor. It can be confirmed that the sensing element is fixed in the PDMS while maintaining the standing position. While the energy strain gauges were defined as R1 to R8, the resistance values were approximately 2.5 kilo ohms. Finally, I would like to explain the sensor response to the 6-axis force. Here we show the experimental setup. The fabricated sensor is located on 6-axis load cell for the reference, and the sensor can be tilted by goniometer stage. Also, they are moved by XYZ theta stage. To apply the triaxial force, the XYZ stage was moved. To apply the torque around the Z-axis, theta stage was moved. And to apply the torque around the X or Y axis, biaxial goniometer stage was tilted. Here we show the sensor response to the triaxial force. We evaluate the sensor response to the triaxial force by applying a 0 to 40 Newton normal force and 0 to 5 Newton biaxial shear force while holding with an 18 Newton normal force. The top graph shows the response from the 6-axis load cell. And the bottom graph shows the response from the fabricated sensor. In the response to the Z-axis force, all cantilevers show positive resistance changes. In the response to the X and Y-axis shear force, the corresponding cantilevers show positive and negative responses, and while the non-corresponding cantilevers show the little responses. So all cantilevers show corresponding resistance changes to each axis force as per theory. However, the response variability and crosstalk were confirmed. This is due to the slight deformation of the cantilevers caused by heat generated by CO2 laser irradiation. Therefore, it can be improved by using a shorter wavelength laser with less thermal effect to form the LIG. Next, we show the sensor response to the torque around the 3-axis. We apply the torque around the Z-axis by rotating the theta stage 5 degrees while holding with a 28 Newton normal force, and a torque around the X or Y-axis by tilting the goniometer stage 2 degrees while holding with the same force. Also, for the torques around the Z-axis, all cantilevers show alternative positive and negative resistance changes. For the torques around the X and Y-axis, the corresponding cantilevers show positive and negative resistance changes. So all cantilevers show corresponding resistance changes to torques around each axis as per theory. However, when torques are applied, the axis force and torques occur at the same time. This is because the center of the rotation of the goniometer stage is not aligned the sensor surface. Therefore, by improving the experimental setup, the mixing of the other axial force can be eliminated, and the calculation of the calibration matrix can be facilitated. So these results suggest that the proposed sensor can measure 6-axis force and torques. Here we summarize in conclusions. We propose a 6-axis force and torque sensor using standing LRG cantilevers. The sensing element was easily fabricated using UV laser, CO2 laser, and thermal deformations. The fabricated sensor shows different response to the 6-axis force and torques. Here we show the acknowledgement. Thank you for your